Yes. And we are using the same data set, so let's assume that the best model is a bit more complicated than the one that we did last time. So there are several variables: socioeconomic status, IQ average, that is the class level variable, then COM, and COM is also a class level variable. Then there is an interaction effect of IQ and COM, and we also suppose that this is a cross-level interaction effect, right? IQ COM, and we also suppose that I have a question for you about Andrei Yurievich. Please remind me about it, okay?
Mm-hmm.
Thank you. And we also suppose that the effect of IQ varies by class. So, okay, let's look at what the model looks like. So, random effects are, this is the intercept, this is the IQ that varies by class, this is the unexplained residual variance for individuals within classes, and then there are quite a few of fixed effects. This is the general intercept, or grand intercept, this is the effect of the socioeconomic status, this is the effect of the IQ average, a class level variable, this is the IQ effect, this is another class level variable combination, and this is the cross level interaction effect. So this is a bit more complicated model. Now, we could also do summary of coefficients. If we do all coefficients, it will, of course, be huge, but let's do it. so that you know. So there are 133 groups, right? So this is the model for these different groups. So there are different intercepts. Then this is fixed, not random. So, right? This is also fixed. But this is not fixed. As you remember, IQ was allowed to vary by class, so this is random, and the effect of IQ varies by class. The combination is a second level variable, so of course it is fixed. Can be otherwise. This is fixed. So, right. Okay. So. Of course, as I said, it might be possible to place all these in a single table of coefficients, but it will be extremely hard to read and not very useful. Yana Mikhailovna Roshina, who some of them may know, was the representative of the Moscow government in St. Petersburg during the diploma защиты, what you call it? Defense, thank you. And one of my students presented simply visual effects of, and she demanded that he presents the table. The table was of course messy, but he was shy and he didn't defend himself, so he got satisfactory. But people who deal with multi-level models probably know that, of course this is possible to put, in a presentation or in a diploma, but it doesn't make any sense. So there are also special functions instead of coef. Coef is a general function that is available in pretty much all models in R. But in this type of models there are two additional functions, ranf for random effects and fixf for fixed effects. So we can also call all random effects. Sometimes it may make more sense because you see that fixed effects are the same for all groups, so it doesn't make sense to do such a large table, but of course random effects are different for the groups 133 pairs of coefficients. Right, so ran f may be better. We can also do fix f. For some reason I didn't do it. Yeah, and so this in combination with ran f pretty much does it.
Is that a variation around the mean intercept and slope random effects?
Oh, random effects. This is a good question. Yes, these are etas. That is, these are what you have to add to the fixed effects. So, yeah. So, for instance, IQ. This is not beta, but this is something that you ought to add to the fixed effects of IQ to receive the ultimate beta, the slope. Okay. So these are etas. These are etas.
And in which case should we center the variables? Maybe it's the right time for this question. In which case we need to center the variables? Center.
Oh, center. Typically, it's done most of the time. It's a good idea to center your variables, because then it would be easier to interpret your coefficients, because otherwise the meaning of the intercepts in particular depends on their observed range, and if it is far from if the zero is far away from the observed range, then the intercept doesn't give you much information, right? So when you center the variable, intercepts become more meaningful, and because intercepts also correlate with slopes, as I explained, right? Usually the correlation is negative. Then even the slopes are a bit easier to interpret if you center the variables. Of course, you can. There is another question: can you center all variables? Like, for instance, what do you do with categorical variables? And can you center gender? Sometimes some people, but some people do it. Well, but maybe it's going a bit too far. But anyway, it is good to remember when you interpret the coefficients that intercept is the value of y when all other variables are zero.
For instance, if we center individual level variables, in that case we need to change our interpretation, because this is a relative in relation to the average level in the group, in our case in a class.
Say again, please.
Oh, if we center individual level variable around group mean, that changes our interpretation.
Right. Well, it's also a question and an option. Do you center around the grand mean, or do you center around the group mean? In this case, in this case, yeah, it is centered around the grand mean. So then the interpretation is pretty much straightforward for the effects. But sometimes people prefer, in certain cases, to center around the group mean, exactly because they want to get a relative effect. Yeah. So there are various ways to visualize the effect. So this dot plot available in the lattice package is a basic way to do it. but I will show you perhaps also a better way to do it. Just a moment. So this is what it does. Because there are so many groups, the ID groups are blurred, and you'll have to work to minimize the size of the characters here. But this is what's done automatically. This is fixed, but you can change it in lattice. What you have here is the blue dots represent the random effects for intercepts, and blue dots here represent the random effects for IQ. As you can see, and then these lines, segments, black segments, represent the confidence interval. That is basically portraying how much the random effects differ from each other. And you know, if the two confidence intervals intersect, then they probably are not different significantly. When they do not overlap, then it means that there is a significant difference. Now, if you look especially at the IQ, you see that there are only a couple of points that are different from each other. Right? In most other cases, you know, the effect is pretty much similar, and the confidence intervals basically overlap. With the intercepts, it's not the case. So it looks like you know, the intercepts sometimes are quite different. Like this intercept is definitely different from this intercept. So the classes differ by their means, but perhaps they are not so much different by the effect of IQ on the grade. The reason why this model turned to be better than the model without the random effects for IQ is perhaps the effect of a couple, or maybe slightly more than a couple classes that are different from each other. And if not for the effect of those few classes, then the effect of IQ might be considered similar. Okay, so I don't recall what I'm doing here, but oh, I see. I'm trying to before I show you another plot of the same kind, I try to for some reason there is no SJ plot thing in here. I have it on my other computer, I'm quite sure, because I checked it yesterday. So I could show you after the break. It is a much nicer plot. It's of the same type, but it gives you better information. But it is from another package.
How do we know what is significant and what is not significant from the plot? Because I saw yesterday in a journal the significant coefficients were with different points, and the insignificant were also with different points, and not with the confidence intervals.
Well, if confidence intervals do not overlap, then it is for certain that there is a significant difference. In other cases, the overall, you know, the overlapping confidence intervals do not necessarily mean that the effects do not differ significantly, because there are, you know, maybe many of them, like 133, and the differences between each pair might be small, but the overall accumulated difference, if you will, might be significant enough to make it a good idea to include this difference in the model. And this will be shown by by chi-square coefficients when you try to decide which model is better than the others. And if the chi-square coefficient shows you that you better include this random effect allowing for random slopes, then you probably need to include the random slopes. That's basically the rule. But there is a graph that I want to make to show you how the multi-level model works. So it's another way to visualize and make sense of the multi-level regression, but the script may be a bit complicated. So first I find out the range of IQ. It varies from -8 to +6. Then I find the IQ average, the class level variable, and it is from -5 to about +2. The mean of IQ average is about 0. I do histogram of IQ average. It's a little bit skewed to the right. That is, there are some outlying very bad classes. And these outliers probably, you may guess that they are probably responsible for the significance of random effects, right? Because if there are several classes in your models that are different enough to warrant the inclusion of the random effect for slopes on IQ, for IQ slopes. Then there's, on the other hand, the individual IQ is not so skewed as the okay, I remind myself what the data looks like. This is the first line of the file. I attach the data, and then I do a search for interesting cases that would contrast with each other, because essentially there are in this multi-level model, what matters is the IQ average, right? So some classes are smart, some classes are medium or mediocre, and some classes are dumb. And then the second variable that matters here is the whether the classes combine and combine. So what I want to do is a matrix of graphs, like showing 6 multi-level, 6 classes with the multi-level regression in them, and see how the distribution differs in these contrasting cases. So I want to take a couple of smart classes that would be different whether they are combined or uncombined, a couple of dumb classes, and a couple of mediocre IQ classes, and see how the effects are different. So I simply search for an interesting case from a group where combine equals 0 and IQ average is less than -1.5. This is a dumb class which is not combined, and I pick up from this list a number of class, a code for class, and I decide to pick up this one, and I do the same for all others. So I'll skip this. I just look
So you just did it selected manually?
Manually, yes. So the next thing I do is I look at the coefficients. And this is just the first line of coefficients to remind myself about the coefficients that I have in the model. you remember that intercept and IQ are random, others are fixed. And here, by the way, when you do coefficients, it's already summed up. So when you do random effects, it shows you etas, right? That is the component that you need to add to the fixed effect in order to get the coefficient. Here, the intercept and IQ, these are already summed up, so these are like final. So then what I do, I create an object called alpha and f, where I pick up the first column of all 133 coefficients, and this is would be the vector of intercepts. Are you following? Okay, so this is the first line of all coefficients, right? The blue one, right? The blue one. So there are 133 such lines, right? But then what I do to create an object called alpha MF, I pick up the first column, and the first column are intercepts. So there will be 133 intercepts in this object. Right? So these are intercepts. These are random intercepts.
Once more, why 130? 33.
Because there are 133 classes in the sample. There are like more than 2,000 individuals in the sample and 133 classes in the sample. We can look at what it looks like. So these are intercepts. This one is number 129, and this, I guess, is number 133. But over. I took the first column, but because I took it separately, it now is simply a numeric vector. It is simply a numeric vector of intercepts. Then I do again the fixed effects, and I pick up the sixth fixed effect. The sixth fixed effect is the cross-level interaction effect. Okay, I will need it later, but I'm not saving it at the moment. I just show you what it is, because I will use it in my graphs. Now, T applied returns a table of means of this variable for each class. So there are some students who are, let's look what it looks like. So its length is also 133, and this is what it looks like. So some of them are 0, that is that they are uncombined, and some of them are 1s, meaning they are combined. Right? So then I create a vector called beta IQ, which is beta coefficient number 4, right, plus fixed effect number 6 times com. So what is it? This is the see, the effects are different because of the interaction effects. So when you have an interaction effect, what you do is you add your beta and your beta for the interaction effect, depending on whether the other variable is 1 or 0. For the 0 you do not add, and this means that it is simply beta. And if com is 1, then you have to add this interaction effect to the beta coefficient at IQ, right? So you see what I'm saying?
Yes.
I,
It's very simple. It's not hard. So we have beta 4 times IQ, and we have beta 6 times IQ and com, right? Now com is a dummy variable. It takes the value of either 0 or 1. So if it is 0, then the effect of IQ is simply beta 4, right? So we can write like partial equations. Com equals 0, then the effect of IQ on grade is beta 4, right? This is the effect of IQ. And if com equals 1, it means that the effect of IQ on language is beta 4 plus beta 6, because if this is 1, right, so we have beta 6 times IQ. And we have IQ here and IQ here, and two different coefficients, and then we can put them in parentheses, right? So we have beta 4 plus beta 6 times IQ. This is what I mean. This is what we are doing. Because we have, I'm going to do this set of graphs, like this. There will be 6 graphs. So there will be com0 and com1, and there will be dumb, medium, or smart, right? And for the slope for combined classes would be different from the slope in uncombined classes, right? So in order to take this into account, I have to, get the coefficients. So this is what I'm doing here. So I'm taking the fourth coefficient, and so I create a vector called beta IQ. Just let's see what it looks like. So the first one is 202, and alpha is 42. So this is the intercept and this is the slope. I mean, this is the intercept and this is the slope for the same class, number 180. This is the ID of the class, the class ID. We have names for alpha. Oh no, we don't have names for alpha, but we have names for beta. But they are in the same order. So I can assign names from beta to intercept if I want to, right? So this is one possible way to handle this. This is what I could do, to assign names to the intercepts from names of the betas.
and why do you need names?
Because when I will be doing this set of graphs, I will need to identify each graph by its class name. So, but it might be possible to do, but I'm not doing it. I need just having one vector of names would be enough, but I could do it. And now I'm doing a loop. Do you know what a loop is? Yes. Everybody does.
It's a circle.
A loop, petля in English, but in Russian programming we call it cycle. Cycle. But, so when you do a loop, you execute a set of commands for as many times as you need. But in order to do a loop, you need a counter, счетчик in Russian. Something that helps you identify each step of the loop. Okay?
It's like interactions.
No. It's a programming thing.
It's programming.
So
yeah.
I want the program to execute a certain sequence of commands several times. So there is, in this particular case, I want to build 6 graphs. So I write up the commands and for a graph, but I want to the program to repeat this 6 times. Not just one time. I could do it also manually, but you know, typing 6 times all these commands is tiresome, and sometimes loops are helpful when you want to save a little bit time. So this is what I'm doing. I create a vector called display, and these are the ID of classes that I selected manually. Remember how I did it? I simply looked at the ranges and then combinations of variables, and I selected 6 classes. These are the numbers of classes, the ID numbers of classes that I selected. Then the next command par is for parameters. It's a graphic command that controls, there are many arguments that are possible in par that select, that control globally the type of lines, the colors, and many other things. In this case, I'm using just one argument, mf row. It controls how many graphs I want to put on the same page. And here, I'm saying that I want 2 rows and 3 columns of graphs, which means 6 graphs on the same page. Okay, so it opens a graphic device, but so far it is empty. But then for each new command of plot, it will put a separate small graph until there are 6 graphs. Okay. Then this is the loop. I wanted to say the cycle, but it would be the Russian cycle, the loop. So these curly braces enclose the set of commands that I want to use repeatedly, and this is the counter. This is the counter, счетчик. So the counter opens with the command called for. J is a virtual variable. It doesn't exist, but this is the counter. This is a variable that will exist. In display 6, and this is a numeric vector. It expects a numeric vector here, and the numeric vector is this. So there are only 6 options. So the counter will be used 6 times, right? And all the commands here will be repeated 6 times. Right? So then let's examine the commands. So plot is a general graphic command. In this case, it produces a scatter plot. Right? The first argument in the plot function is the x-coordinates. Abscissa. What is the word for abscissa in English?
X-axis.
X-axis. Yeah, that's yeah. These are coordinates on the x-axis. These are the coordinates in the y-axis, right? So these are two basic arguments that are needed to do a scatter plot. Now notice that I plot IQ on the x and the grades on the y-axis. So it's basically a graph showing how the grade for language depends on IQ. So this is right, but then I don't use the whole vector, but I use an index, right? I use only those observations for which the class ID equals j. So on the first step, when this command is done for the first time, j will be this, and this is the same j, 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 right? And but when this curly brace ends, then the command will be repeated again for the next j. This is for this, right? So so let's examine the plot further. So these are two basic functions. So I plot language against IQ. I give the label to the x-axis IQ. The label for y-axis is language score. Could be something else. Well, I could write anything in the quotation marks. I notice I use xlen and ylen arguments that control the range of x-axis and y-axis. Why is that? Because normally R wants to optimize the fit of the plot so that only the observed range is included. But I want to use the whole range for each of the 6 graphs, so that would be easier to compare. Because otherwise, you see this box of graph would move depending on the observed range, and the comparison would be not as straightforward if we use the same range for all 6 graphs. Is that clear? This is the size of text on the labels. This is the character type, point character. PCH means point character. There may be triangles, there may be field circles, there could be empty circles like rings, there could be squares and many other things. I use one particular point. I use the size of points. And now this is the title of the graph. The title of the graph is J, which means the ID class. The class ID, I'm sorry, the class ID. Okay. So this is the first command that I want to execute for each class. The second command is AB line. Now AB line builds a straight line using 2 coefficients, the intercept and the slope. Therefore it is called AB. It's like in high school, A плюс B равняется C. Right? Right. So it needs 2 coefficients. So I give it 2 coefficients as the 2 first arguments. So this is the first coefficient. So I give it the vector of intercepts that you remember I created a vector of 133 intercepts. But of course I don't want to use all of them. I need only one. So I make it like this. Names beta IQ equals J. Remember what names are? Well, these are ID classes because the vector of beta intercepts is named. Right? Notice that I do alphas here, but I use names from beta because I didn't assign names to the alphas.
But why you can't say class G equal G? You can't say here like in previous.
Because we are still using names.
So you just can't say alpha MF class equal G.
I guess yes, it would be also possible.
Yeah.
I just didn't occur to me, but yeah, I think that would also be possible.
Mm-hmm.
But this is how I did it.
Yeah.
And then this is the second coefficient, and of course it also from this class. And the last argument I use is color. I want the regression line to be of red color. Could be also color J, but then but then I would have to use an additional argument like rainbow, so that the but it doesn't matter.
Or a vector of colors.
Vector of colors, yes. But so I execute this cycle, and apparently it worked. And let's look at the graphics window, and this is what I have. So this is something that helps you visualize the multi-level regression a little bit. So we have 6 classes. The main title for each graph is the class ID, and you have the same range of IQ and the language score on all 6 graphs, which helps you identify which class is dumb, if you don't remember it, and which class is smart. So where are the dumb classes?
On left.
On the left, of course. And the smart classes are on the right. See, they are it's good. The distribution, and these two are the median classes. Okay. And now, where do you think is the row with combined classes, and where the row is the uncombined?
This one is combined.
Yeah, the bottom row is combined classes, because there you can see that the slope is greater. The slope is greater for a reason in combined classes. Okay, so the bottom row is so this is something that you could picture. Notice how it also shows you incidentally how multi-level regression works. Look at this graph. So the straight line, if we only had this class, should have gone here, right? But it goes here. Why is that?
Is that corrected for like a number of cases?
Yes, this is corrected for first for the number of cases, and secondly for the grand intercept. For the grand intercept, because this is a particularly bad class, it seems, but the number of observations is small, and so the multi-level regression says maybe I don't want to trust these observations fully, and I recall that the general intercept is someplace here, so of course this is a dumb class, therefore I have to move it down, but perhaps not by as much as this class observations suggest, because the number of observations in this class are small. So this is a feature of the multi-level regression. It sort of corrects for sample size, for group sample size, and for fixed or grand intercepts and grand slopes. All right, so I really wish I had this SJ plot, but these are only 2 lines, but can we do it like after the break? And then I'll have logistic regression. Okay, so like 5 minutes, 10 minutes.
5 minutes.
Let's just switch on при IQ. Он, значит, имеет смысл только для 2 классов. Да, да, он пока почти незначимо. Но интерцепт, вот мы видим, что вот это и вот это, они серьезно отличаются. То есть на концах распределения. Ну вот это гораздо лучшая картинка. Так, ну, наверное, других надо раздать.
Yes, it's but not here.
So the other plot that I wanted to show you is done using a package called SJ plot. There are many things that this graphic package does. So there is a function in this package called SJPLNER. That is, these are graphs for multi-level models. This is the name of the model. Okay. Type RE means random effects. So plot random effects. Sort coefficients by intercept, because they can be also sorted by betas, not necessarily by alphas. And this is also another neat argument. Fade non-significant equals true. And this is the graph that we get. So the red ones here are less than average, or 0, and blue ones are greater than average. For the IQ beta coefficients, this is the other way around. But the fact that non-significant effects are faded is very helpful, because you can see, especially in this graph, when you have beta for IQs, that there are only 2 classes. This one and this one that have significantly different beta coefficients from the rest of the classes. So if these 2 classes were deleted, the differences would be insignificant. With regard to intercepts, though, there are many more significant intercepts here and here on the 2 ends of the distribution. So this is rather helpful. You wouldn't be able to see really on that other plot that is produced by the lattice package. But this is what I wanted to show you as far as visualization of random and fixed effect models is concerned. So are there questions, or can we just switch to?
How to sort by default?
Oh, then you really point the see. Then you show IQ, like here. This is basically intercept, and parenthesis is how these coefficients are stored. This is the name of the storage in LNER. Intercept is in parentheses, and other coefficients is just the name of the variable. So instead of intercept in parentheses, you would have put IQ here, and you would get sorted by IQ effects. you can also do this, I guess. It takes a bit of time, but okay. And now let's see at the graph. So now this is the significant effect, and this is the significant effect, but the intercepts are not sorted. It's sorted by IQ now.
Can I ask you, the red stands for the negative and so the as for the colors.
Yeah, yes, they distinguish between positive and negative effects. For those variables which is it sorted by. I mean, for those effects which is the by which it is sorted. In this case, the betas. And previously it was alphas. Okay, then we'll move on to logistic regression. I guess I will say a few introductory words just to make sure that some basic things about logistic regression, and then in general, and then I will show you a couple of examples how to fit logistic multi-level regression. But it is not in principle different from linear multi-level regression. The most important difference is that it takes a lot more time because it takes more computer resources. These are more complicated models, they are non-linear, they are estimated by maximum likelihood also, just like linear models, but the same method, but they are more difficult to. Okay. No, I meant the lecture. These examples I will not even. Really? PDF. Yeah. Thank you. Okay. So, general linear model includes linear regression and ANOVA, also ANCOVA. ANOVA, for general linear model, the dependent variable has to be normally distributed. It is a continuous, normally distributed variable. This is a must, absolute must. So if it is continuous but not normally distributed, you have to transform it. So before you can use a linear model. If it is non-continuous, then you cannot run a linear model. So then, depending on what you have in the set of your independent variables, the general linear model falls into three categories. If all independent variables are discrete, then you have ANOVA. If all of them are continuous, then you have regression. And if it is a mix, it's called ANCOVA, although this term is increasingly is used less and less often. But then the other class of models is generalized linear model. It covers many nonlinear models, including logistic regression and Poisson regression. And for the logistic binomial regression, the relevant R function is GLM. So rather than LM, which stands for linear model, you do GLM, generalized linear model. And then there is an additional argument family binomial. You remember family Poisson, right? And in this case, family binomial, which tells the program that the dependent variable is binomial.
Can I ask you, what is the difference between the general and generalized models?
Yes, general linear model is a linear model. Generalized linear model is intrinsically a non-linear model, but we use a link function to connect the linear term, alpha plus beta x, to y. But without this link function, it is intrinsically non-linear. So the basic idea that generalized linear model links the regular linear term to a link function. In the case of logistic regression, the link function is logit. So this is a reminder of what a logit is. So if we have probability of success running from 0 to 1 by 0.1, then for each probability of success there is a probability of failure, which is 1 minus p, right? And it runs, of course, from 1 to 0 by 1. And then there is an odds ratio, which is p over 1 minus p, right? And it runs from 0 to essentially infinity. So as the probability of success approaches 1, the odds ratio becomes increasingly greater, but if it is exactly 1, then the odds ratio is not defined because you cannot divide 1 by 0, right? Then if you take the natural log, this is a natural log, in the Russian notation it would be ln, but in English it's simply log. If you take the log of odds ratio, then you get the logit. So let's look at the distribution of logit. So when probability of success is 0.5, then probability of failure is also 0.5, and the odds ratio is 1, because probability of success is the same as probability of failure. Now log of 1 is 0, right? Because exponent of 0 is 1. So these are inverse functions, right? Exponent and natural log are inverse functions. Now the logit for probability of 1 is not defined because odds ratio is not defined. And odds for probability of success of 0 is not defined either because log of 0 is not defined. Log of 0 is not defined. But if you look at the distribution of logit, it is centered around 0 and it is symmetric, right? So you get exactly the same values, except that they are positive here and approach plus infinity or minus infinity on this end. Right, so this is logit. Now, why do we need the logit? Consider a simple example. So what happens if we plot y, which is binomial variable, against x, which is continuous? So this is the case for logistic regression. Why can't we use the linear regression? Well, let's pretend that this is the probability of electoral success, either one, not probability, but actually success. 1 is success and 0 is failure. So the candidate either gets elected or does not get elected. Right? And the x is the amount of money he invested in, or she, in her presidential campaign, which is not the case in Russia, right? So all observations fall essentially on 2 lines. I jitter them a little bit around so that you could see that there are 2 observations here rather than 1, but actually they are exactly on the same spot, right? So, okay. You could potentially use the linear regression, and it would look like this, and then it wouldn't be very meaningful, and also many assumptions of the linear regression would not work here because there would be the error would be biased, there would be systematic rather than random. It will be not normally distributed. And then there is a whole range here and here that doesn't make sense, or even here. What does it say that, probably it could be interpreted as probability of success. But, well, so what people do in this, or what we might do, is instead of y here, use the probability of success, the observed probability of success. And how can we calculate the observed probability of success? This is the formula. There is n with an index h. N is this sample size at the particular level of x. So to help you see how this formula works, let's calculate the probabilities of success ourselves. So I'm not sure what the units of money here is, but let's pretend millions of dollars. So if a candidate invested $5 million into his campaign, what's the probability of success?
It's the number of
Yeah.
cases divided by total number.
Yeah, it's sum of number of sum of the y's divided by the number of observations. So we have 3 y's. All of them take the value of 0. 0 plus 0 plus 0 is 0. Divided by 3 is 0. So the probability of success here is 0. He invested $10 million, then the probability of success becomes 1/3. Yes, then 1/3, then 2/3, then 2/3, and then if you invest enough money, then the probability of success is guaranteed. It becomes 1. I don't know if you remember the 1996 presidential elections in Russia, or you are too young to remember this. 1996, Yeltsin ran against Zhuganov. Right. In January 1996, Yeltsin's approval rating was 3%, I think, or 5%. And in June, he won the elections. But meanwhile, at the presidential administration, some people, carried Xerox boxes of dollars with them. So huge amount of money was invested into that campaign, and success was guaranteed. All right. So what we do on the second graph here is that we, instead of y, we plot probability of success that is calculated against this, according to this formula. That is, at 5 we plot 0, at 10 we plot 1/3, then 1/3 again, 2/3, 2/3, and 1. And now the linear regression looks a lot better, right, compared to this. Unfortunately, it's still not good enough for several reasons. I will not list them all, but the major one is that the probability function is intrinsically nonlinear. It has the so-called floor effects and ceiling effects. To help you understand the ceiling effects, consider the amount of resources you need to invest if you want to move your candidate's approval rating from 49% to 51%. So there is a 2% difference. Let's say you have to invest $2 million, $2 million additional dollars to do this. But then there is another task when your candidate's approval rating is already 95%, but he's so crazy that he wants to have 97%. So 2% more. It seems like it's the same 2%, but it's not the same 2% because all possible people who could have potentially approved the candidate have already approved your candidate, and so those people who are in the 5% opponents are really staunch opponents of your candidate, and it takes a lot more resource to persuade them. Maybe at the gunpoint they will do it, but not all of them. So that's a more difficult task and requires a lot more resources. And so this is called the ceiling effect. so at the upper end of the distribution. But you have also a similar effect at the problems with the linear approach. So yeah, regression must be limited to the range of 0 to 1, residuals will be normal. The most important is this, that the probability function is intrinsically nonlinear. It is approximately linear in the range of 0.2 through 0.8, and there are ceiling and floor effects otherwise. However, logit is a linear function of x, and this is why logit may be used in this sort of thing. Another possibility is a probit, which is the inverse of the normal cumulative function. So there is a whole class of probit models. But the difference between logit models and probit models is not, I mean, it's a matter of liking. That doesn't mean much. Logits are perhaps more popular in sociology than probits, but some other disciplines probits are used. So this is how the logistic function looks like. So you see it's sort of S-shaped, and you know, this is basically the ceiling effect, and that is the floor effect. So approximately linear distributed here. This is the ascending function, and this is the descending function. And so if we link logit to x, it's a linear function. If we link probability to x, it is nonlinear. It is this is the logistic function. So there is a linear argument, but it is linked to probability in a somewhat complicated fashion. But this is how you calculate expected probability, right? But if you link logit and x, they are linked by simple linear expression. So how do we interpret the beta estimate in the logistic regression? Actually, it is difficult to make sense of it, since logit is a linear function of x. B shows the change in logit when x is changed by 1 unit, but whether it is helpful or not, probably not. So I suggest a simple rule of thumb. Look whether B, which is the estimate of beta, is significant and disregard it otherwise. So this is very simple. And if it is significant, then see if it is negative or positive. And this is also very straightforward. It is easy to interpret, because if it is negative, it means that increase of x decreases the probability of success, whatever it is. And if it is otherwise, then it is otherwise. So a binary logistic regression estimates the probability of y, taking the value of 1 given x equals a certain level via logit as a Boolean function. So we really do full equation. Instead of linking y directly to this linear expression, we do logit of probability of y. So there are two steps here. So from y we get to probability of y, and from probability we get to logit. And only then we can link it directly to the linear expression. Okay. I hope this is clear. And if it is clear, then we probably want to go to this example. Can I simply click here, or how do I do?
No, you can do it, but if you're opening the R studio.
No, can we do something to open this in R? Oops. We have too many Probably don't need this. And can we do it again? See, Anna is not only using Windows, but she's also using the what is it called, file commander.
Yes,
Uh,
total command.
I'm not a Windows user, but I'm okay with Windows, but I don't know the commander. Okay, and all right. Can you see it? Because I previously used the larger font.
It's okay.
It's okay. Okay. So this is more or less according to chapter 14 of Gelman. I'm trying to reproduce his example, but I don't have his data, so I'm using other data, and therefore coefficients will be slightly different from the coefficients that are reported in his book. You know Andrew Gelman's book on multi-level regression. He's the author of the ARM package also. So
Yes, I need to change the name.
Possible? Like the big large.
yeah,
Like there's
а можете вы закрыть скрипт вообще пока? Да, закрыть.
Свернуть?
Нет, закрыть. Вот. Теперь я сделаю вот так. И вот это будет, наверное, приятнее видеть. Вот. А теперь можно открыть и скрипт, и там, чтобы там был этот файл.
Faster to change working directory. Could be easy, I think.
Okay, let's change the working directory.
I don't know how to change it here. Should I do it manually?
Where is this S4 located? I mean S5 here, right?
Yes. Then let's use this one just to change slashes. Of course,
It's all right.
we will do this.
Как?
Yeah. And by number.
Ah, yes.
Yeah,
They all should look like this.
I think it's sometimes, yes. Try to
Okay.
turn it off and turn it off.
I
Mm.
don't know.
Maybe it's better to do just manually.
Yes.
Mhm. All we need is to place the files in this. Where are we? Incidentally, where are we? if it's possible to place this file.
I don't know why I have the same problem in our studio. With our studio I can do it using interface. Sometimes it works.
Еще одно. Потому что бином MLM она называлась, а не байномиал. Поэтому невозможно было сменить. Название неправильно. Неправильно. Now we are okay. And okay. It's a large file, so it takes a while to read it. Then this is National Election Study of the United States that represents the results of national elections for a long period of time. And I pick up only 1 year, the election of 1988. This is the data from CDS poll. Then I test the file, I look at the file names, there are many. I look at how the presidential vote is coded, and so there are several options. 0, but there are 0 observations. 1 means Democrat, 554. 2 meaning Republican is 618, and there is a third major third-party candidate. For instance, in 1968 it was Wallace. It is 0 in 1988, so it is essentially a binomial variable, right? But there are two empty categories that we really do not need. Okay, library car. There are other ways to recode, but this is what Gelman does. He uses this recode function from the car package. I would do it differently, but this is what he does. So this is the recoded variable. 554 voted for Democrats, and 618 voted for Republican candidate, who was incidentally in 1988 George H.W. Bush, Bush the father. I think this is already okay, this is Gelman's package. Then notice how we do the logit regression. It's basically one additional argument. The function is the same, but then there is family binomial, and then link is logit, because link can also be product. This is how it's done. So this is essentially an empty model, so I call it M0. What does it say? And I know that there are no explanatory variable, but we believe that there should be state differences. That is, the means of votes for, Bush depends on the state. Right? This is what this is. So essentially, the logic is basically the same as in linear regression. Nothing different. Okay, it asked me to use GLME, but actually it has executed, but this is GLMER. But it is already executed, and it's right. It is more correct to use GLMER in all of this. This is it, I think. There are only 3 models in this example. So let's look at the summary of the model. It's a copious output, but essentially there is a fixed effect, which is the intercept, and this is the grand intercept, right? Just like in the linear regression, the grand intercept. And there are, pardon?
This is better, not exponential.
Right, and yeah, this is the data. I think in my notation, and also Gelman's notation, and also Doomer's notation, they will be called gamma. So this is gamma 0, 0. But essentially, yes. So this is the grand intercept. Then there is a random effect, which is the intercept for states. There's random intercepts. But we could also do the display function, which is a shorter summary function written by Gelman as a part of his R package. Well, if I use GLMER, it will be shorter, because all this is just because I used LMER. But nevertheless, so these are the 2 random effects, intercept for each state, and the unexplained residual variance of individuals within states. Right. And there is one fixed effect, which is gamma 0, 0. It's estimated as 0.1, and it has this standard error, which means it is not significant, because if you divide the estimate by standard error, it's about 1, which is not significant. So it's close to 0. It's close to 0. Close to 0 here means that the vote is close to 50%.
The ratio.
Right, exactly. Yeah, because exponent of 0 is 1. It means that the odds ratio is 1, that is probability of voting for Republican is the same, almost the same as the probability of voting for Democrat, and in fact those elections were quite close. Okay. Let me refit it just in case for GLMER, so that I would not have these reminders. Okay, then I do another model, call it M1. We have predictors, black for black race, and female for gender. So these are individual level variables, and then this still says that the intercept